let it run. So I guess the first is a bookkeeping thing. Apparently, when I created the vector lab, I did not proofread it carefully. I might even say it didn't proofread at all. I just had faith in the system. And my apologies, there are two figures that are missing. So for procedure A, problem 2 and problem 3, there's a figure missing where they actually show you what the vectors of A, B, and C look like. So I have now posted those two pictures. I haven't redone the document itself, but I did post the pictures in Blackboard, so you should be able to see them. And did I say when that lab was due?
Thursday.
Thursday?
Yeah, it was Thursday.
Okay. I'm still good with that, but occasionally I have students who their time to work on it would have been before today, and they won't have that opportunity again because of work or other obligations. So if you're in a situation where Thursday is unreasonable, since I did not provide everything in the lab that you needed, then just talk to me individually. All right, so we'll start out with the traditional, are there any questions? Besides the master set number 3, problem 16 or 8, because I'm going to talk about those.
In the homework, when it uses 10, we're supposed to use 9.8, right?
For, you said in the homework when it says?
10.
Oh, 10.
Yeah.
Okay.
Like number 65 uses 10. We're supposed to use 9.8, right?
For the homework quiz, either one.
Either one's fine with the quiz.
Yeah,
Okay.
on tests, use 9.8 unless I state otherwise.
Okay.
Assuming it's on Earth.
What did you say?
Assuming it's on Earth.
Okay, okay.
Yeah, because problem number 8 takes place on Mars.
Gotcha.
So 3.7 meters per second squared is good enough. I did not provide the acceleration due to gravity for Mars on the homework. That's the kind of thing on a test or quiz, that the in-class test or quiz, it would be at the top of the first page, or you would ask and I put it on the board. I'm assuming if you're doing the master set, you would just type in lowercase g with a space, then Mars, and it'll give it to you. At least that's what I did, and it gave it to me. Or you can get fancy and type out acceleration due to gravity on Mars. Other questions before we talk about those two specific problems?
Can I ask a question on the chapter 3 reading?
Yes, ma'am.
So on question number 44, I was a little bit confused by the ball weights and drop.
All right, let me go grab my book. Chapter 3. Is it problem 44? Okay. So your question?
I didn't get the question.
Oh, okay. Assume that these are all taking place, let's see, they talk about 3 balls of different masses are thrown straight upward with initial speeds as indicated. I am making the assumption that they are all basically thrown from the same height on the same planet. That's the assumption he's making as well, based upon the answers. chapter 3, problem 44. So the first one, A, is going initially at 10 meters per second, and it's 1 kilogram. B is going up at 15 meters per second initially, and he actually does draw the vector longer as appropriate, 1.5 kilograms. And C, 3 meters per second, and 0.8 kilograms. The mass of the ball is irrelevant. If the question were about how much force is required to get them to get to that speed when you throw it, then it matters. But here, they're already in the air. We'll set up the chart. So at time 0, time seconds, 0, and the velocity of A in meters per second, 10. This one, velocity of B in meters per second, is 15. And the velocity of C in meters per second is 3. What is the acceleration going to be?
10.
Okay, or if we were more precise,
9.8.
meters per second squared, all right? So my acceleration, and what's the direction of the acceleration?
Down.
Right. Acceleration is downward, so considering I've written these as 3, 15, and 10, I'm sort of implying that up is positive, because these are all initially thrown upwards, and that is a 15 right there, the one sort of got lost. So up is positive, so my acceleration therefore is negative 10 or 9.8, whichever one, meters per second squared. Which means that my velocity changes 10 meters per second every second. Sorry, correction. My velocity changes negative 10 meters per second every second. Because this is the change in velocity over change in time. So this would mean negative 10 meters per second. So after each second ticks off, I'm going to subtract 10 meters per second from the velocity. So after 1 second, what is its velocity?
0. 5.
-7.
And what the heck, let's just do one more. I don't think the problem goes to 2 seconds, but yeah, they're just talking about 1 second.
-9.
-5.
-17.
All right, so part A, first off, is asking about rank the speeds of the ball 1 second after being thrown. Now, what we have on the board here are velocities, which means it is a vector, which means we're dealing with a direction. The minus sign is telling us direction. Speed does not care about direction. If the policeman has a radar gun on you, it doesn't matter whether it's going away from him or towards him. It's going to register a speed there. I would find it interesting if they actually had velocity guns, just so that they'd also have to write in the direction you were moving relative to something. So the speed is just the magnitude. It is going 0 meters per second, that's its speed. It's going 5 meters per second, and it's going 7 meters per second. The negative sign is telling me downwards. This one has already hit the peak and working its way back down. So the ranking for part A would be C bigger than B bigger than A. If he had said 2 seconds, well, C is still the fastest, then A, then B. Just bonus, that this was not actually part of the homework. So we'll start out with just, that's question question A right there, I guess, starting with you, Hope. Any follow-up question?
So your formula is time times seconds over what?
So which formula are you talking about? You have,
The formula you use is, like, how did you know to put that over that times that? So what's your formula? That
I
you
know
put
that-
all your numbers
I
in?
guess the formula at the heart of it is acceleration is the change in velocity over change in time.
Okay.
That's the essence of it. Or if I multiply both sides by time, my velocity, change in my velocity is acceleration times time. Hewitt writes, in terms of speed, the speed acquired, instead of change in speed, he calls it the speed acquired is acceleration times time. Other question on part A? And then part B is write the accelerations, but they're all the same. That's the assumption we took when we actually entered this. Personally, I prefer if you'd switch those, but you didn't. But acceleration due to gravity, we take two objects, we did it on the first day, I think, or second day. Take two objects of different masses, drop them, they hit the ground at the same time. I guess this is slightly different. But there's an acceleration lab that I don't do every year, in which you actually drop the ball in front of a motion detector and figure out what the acceleration is. You can also throw it up into the air with a motion detector and still calculate the acceleration and show that it's about 9.8 meters per second squared. And if you have time during the lab period, you can play around with that, because you'll be working with a motion detector.
I have a question looking at due dates for this course. It says master sets 4 and 5 are due this Friday. Is that still correct?
I would like to keep that. I guess Thursday I'll find out if that's a little bit unrealistic. So, because the toughest part of the whole Newton's laws are chapters 2, 4, and 5. And there's a lot of stuff that we have done in the chapter 2 master set that probably, if I thought about it, I would move to the 4 and 5 master set. So I feel like the 4 or 5 master set is shorter, and I feel like you've done a lot of the hard stuff already. But again, if there's something about your personal situation, just talk to me, or I will find out on Thursday if I need to change that. All right. Hope, did you have a follow-up question to this?
No, I'm good, thank
Okay.
you. I just wasn't sure what formula to use, but as soon as like the weight didn't matter, I think I got so caught up on like figuring the weight into that I just got overwhelmed. So as soon as you said that and wrote down the formula, I'm good now.
Okay.
Thank you very much.
Other questions besides 16 and 8? All right, so let's talk about 16 and 8. Why don't we hit 8 first? Because the math people tell me that comes before 15. So basically we have an object that is dropped, and it's gonna hit pavement. I give the distance from where it is initially to the pavement, and I'm gonna use different numbers than potentially, unless it just happened to forget what they are, which I probably have. I'm just gonna use different numbers so that you can just see how to do it, not so that I'm doing this exact problem. So it's going, we'll just say 20 meters. It is on Mars in the problem there, so let's put this one on some planet where G is equal to, 5.7 meters per second squared. Some strange planet, which has things which can drop on the sidewalks. I said when it hits the sidewalk, it stops in I think 5 centimeters on that problem right there, or 5 millimeters, one of the two.
0.5 centimeters.
5 centimeters, so let's make this 8 centimeters, slightly softer. Oh, I gave the mass of the object or the weight of the object? Give the weight, all right. So the object weight is, say, what number have I not used yet? 3 newtons. Now, as far as this problem goes in chapter 3, the weight is completely irrelevant. In the original test problem on which this was based, the weight did come into play at the very end, and we'll just the plan is just do a quick traipse down that lane. Technically, that's a chapter 4 thing. So,
Wasn't it 8 centimeters?
when it hits the pavement, it stops within 8 centimeters of hitting the pavement.
Okay.
So apparently the pavement is kind of soft because it stops in something like that.
Okay. The master set says 0.5, not 5.
Oh, 0.5 centimeters?
Yeah.
Ah. Now we'll keep it at 8 centimeters. Yeah, when I actually thought about what 8 centimeters was, I thought, well, 5 centimeters, that's still rather spongy. All right. So the first one was how much time. Now, because this object is dropped, what is the initial speed of this object?
20 meters.
Sorry,
20 meters.
no, the question, what's the initial speed of the object if it's dropped?
9.8.
Sorry?
9.8.
Nope.
0.
Yes, 0. If it were not 0, it would have been thrown. But it is dropped. Dropping implies that it starts out at rest. So we are pulling from this that the initial speed is 0 meters per second. We can get slightly more formal. By saying that the initial velocity is 0. And the vector symbol over the 0, this is a 0 vector, that's just that, since the left-hand side of the equal sign is a vector, the right-hand side officially has to be. So 0 meters per second in whatever direction you care about. And then it falls. I think I said make down positive. Okay, so I will stick with that one, down positive. So the question is, how much time does it take to fall? And so there is an equation near the end of chapter 3 where Hewitt talks about the distance an object travels if it starts from rest and acceleration is constant. Hewitt writes d is equal to 1/2 gt squared. That's, I think, the way Hewitt has it written. Or maybe he wrote it out in words. I think he actually does the equation. I would write it as displacement is 1/2 at squared. This is specific to free fall, an object that is dropped, that is falling with the acceleration due to gravity. And the equation holds true for any object starting at rest and acceleration is constant. But the problem we're dealing with there is that 20, the distance it falls, is 1/2 times 5.7 times time squared. That's the math problem that I've asked you to solve for the first one. Several ways of going about solving it. One of which, probably the most inefficient, is just randomly guessing times to see until it works.
I can't remember, is displacement relatable to distance? I know
Yes.
displacement has to do with the place you are from your starting point.
Correct.
And distance is how far you traveled,
Right,
right?
right.
Okay, but do they use those words interchangeable or no?
No, they should not be used interchangeably. However, there is a situation where you can kind of get away with it. If an object just only travels in one direction, no veering off, no turning around, nothing like that, just always travels in one direction, then the magnitude of the displacement is the distance. So
Okay.
that's why, since this only goes down,
Okay,
that distance is the magnitude of the displacement.
okay, cause you said you have displacement over there and then you put 20, the distance for displacement, so I was confused. So if it's a free fall or it's going in one direction, it's gonna be the same,
Yes,
okay.
and I never say things that I know are gonna confuse people, unless I talk about quantum physics. But one caveat to that. If I said up was positive, the distance traveled is 20 meters, the displacement is negative 20 meters.
Say that again.
If I said up was positive, here we had down as positive, so it works out, I'm using distance and displacement interchangeably because they're both 20. If I said up was positive, the distance traveled is still 20 meters. But the displacement is you end up 20 meters below where you started, so your displacement is negative 20 meters.
Okay, that makes sense, okay.
Mathematically, it works out because your acceleration would suddenly become negative also, and the negative signs would cancel out.
Okay, that makes sense, okay.
So that equation is the equation for displacement, not distance.
This is the equation for displacement. There's a video where there's another term if you want to make it a little bit more, okay, you don't want to. Hewitt talks about distance, but again, for the same reasons that just talked about with Bailey, that if an object, if it starts at rest, so it's dropped, and it's in free fall, then once you plug in numbers, these two equations look and smell the same. This one tastes a little bit saltier.
But if you throw an object up first, then do you switch halfway?